Welcome to Introduction to Communication Systems. This is lecture 1, part 2. And your lecturer today is Dr. Wilfredo Rivas Torres. As we discussed at the end of part 1 of this lecture, today we are going to cover noise, signal to noise ratio. We'll talk about the channel capacity. What is it that we mean by transmission and channel losses? Modulation and detection, and we'll wrap things up with a digital source coding and error correction coding basics. So let's get started. Noise. Noise is an electrical signal that gets added to the radio signal. Okay, it gets added to the radio signal or information signal as it is transmitted from one place to the other, right? So noise comes, it's a random process. So we don't define noise as a single value, and we'll talk some more about that. Now, noise is not the same thing as interference, right? Interference from other information signals or signals in general, it means that somehow this other signal has corrupted your signal, right? And noise has a corruption type uh, effect on your signal, and it can destroy your information depending on the levels of the signals and the noise, but it is not thought of as an interference, right? Now, for noise is sort of like the static that you hear in your speakers. Think about putting it on a AM or FM receiver. Actually, an AM is really noticeable, right? You get that really cracky noise when you put it in on your radio in between AM stations. Yeah. So the noise level is actually proportional or depends on temperature, and it also depends on bandwidth. Now, that's when we're thinking about the channel, let's say the wireless channel. Now, if your signal, part of its channel includes circuitry, right? So for it to get from one place to the other, you need to go through some circuitry, or just in the transmitter and the receiver, then as you go through the circuit noise, okay, depends on what the current is. It also is going to depend on the gain of the circuit and even the resistance that the signal goes through. Now, I said a little while ago that noise is a random signal. So we don't really talk about noise voltages much. We normally talk about noise in terms of power. So the noise power is actually calculated as this formula indicates, right? The noise power equals KTB. Some people actually call it KTB noise. It's sometimes even called, the noise that we're referring to here is called white noise. So one of the characteristics about white noise is it exists at all frequencies. Okay, so for all intents and purposes, for us, we always see white noise, or KTB noise, as some people like to call it. This formula results in the power being in watts. We do need this physical constant. Everywhere you look at it, they refer to it as K. It's Boltzmann constant, and it's 1.38 times 10 to the minus 3 joules per K. Now, K here is temperature in degrees Kelvin. Okay, notice that you have to put in degrees Kelvin. For example, if you want to do your temperature in Celsius, you need to take, excuse me, if you know your temperature in Celsius and you want to calculate the temperature in Kelvin, you need to take your temperature in Celsius plus 273.15. Okay, and that converts from Celsius to Kelvin. And if you want to go from Fahrenheit to Kelvin, most people convert to Celsius, and then from Fahrenheit to Celsius and from Celsius to Kelvin. But there are formulas for that, and I'll let you guys research that. And then you also need the noise bandwidth in hertz. Okay. Now, bandwidth, we've talked about bandwidth. Bandwidth normally refers to the extent of a signal in the frequency domain, right? In this case, since we're talking about noise, we're talking about the noise bandwidth. So we need to figure out what is the bandwidth that our noise is going to occupy, and that's the bandwidth that we use in this formula. Now, noise power, we typically prefer to express that in units of dBm, which you guys are already familiar from part one. So for example, here's a problem for you. Calculate noise if the temperature is 16.85, and if you're wondering why it's so specific of a number, this is the temperature at which the IEEE defines noise, right? And let's say in the problem, 16.85 degrees Celsius, and the bandwidth is going to be 1 megahertz. So our first step is right here. We want to convert our temperature from Celsius to Kelvin. So we add 273.15 to 16.85, and we end up with 290. So this is the 290. This is that IEEE temperature. Now, noise, we multiply the three factors, right? That we said we need to know Boltzmann constant, the temperature, and the bandwidth, and it comes out to 4 times 10 to the minus 15 watts. Again, here's where you see where dBs kind of come into action, right? That's a really small number. Now let's convert it to dBm, right? So here we go. We're going to do 10 log of that power in watts plus the 30, right? And you end up with a 1 megahertz, within a 1 megahertz bandwidth at 290K, you end up with minus 114 dBm. Now, in the practice, right, we sometimes say, oh, room temperature, right, 16.85, the noise is minus 114 dBm per megahertz. We measure this in 1 megahertz, right? So it's easy for us to have that as a reference. If you wanted to reference it to a single hertz, right? So we could also say that, for example, Pn, okay, equals minus 174, right? And that would be dBm, but then we would sometimes call it per hertz. So within a 1 hertz bandwidth at the same temperature, you get minus 174. And you can see what the magnitude differences are between expressing it in a bandwidth of 1 megahertz versus the bandwidth of just a single hertz. Now let's talk about signal to noise ratio and why do we bother to do this ratio, right? It's because it's a figure of merit for your communication system. In our case, right, the higher the signal to noise ratio, the better the quality of the signal you have, right? Signal to noise ratio, which we sometimes abbreviate as S over N, right, in this way, indicates the relative strength of your signal to the noise in your system. The stronger the signal and the weaker the noise, the higher this ratio is going to be, right? Now, signal to noise ratio is a power ratio. So we were talking about power gain last time, which is also a power ratio, right? But that's output power divided by input power of whatever stage you have. In this case, our ratio, we're going to see in just a minute, or as we've been talking, is our signal to the noise power, okay? Fairly commonly in many data sheets, you will see signal to noise ratio specified as SNR. It's the same thing, right? So here's our definition, but in equation form, okay? And notice that signal to noise is nothing but the power of the signal divided by the power of the noise, which in dB, again, the fabulous advantage of using dB, you just subtract one minus the other, right? Power of the signal in dB minus power. These are both power, so they're both either in dBm or both are in dB watts for you in order to determine your signal to noise ratio. And again, another example, let's say we're at minus 114 dBm at room temperature, right? So that's, we know that our bandwidth is 1 megahertz from our prior example. But now let's say that our signal, right? Our signal has is at a power level of minus 50 dBm. And we want to calculate the signal to noise ratio. Well, minus 50 minus 14 ends up with a signal to noise ratio of 64 dB. Now, the signal communication system signal quality, right? Let's talk about this a little bit. So the signal quality is going to depend on several factors. Actually, the channel has a lot to do with our signal quality. Remember, at the transmitter side, let's mention this, right? At the transmitter side, you're creating the signal, so pretty much the transmitter guys are in control of their signal, right? They understand how their circuit works and everything all the way up to the antenna. Now, once the signal leaves the antenna, you're at the mercy of whatever the channel does or is, right? Signal characteristics, right? Depending on the signal characteristic, things like the bandwidth, there is the impact, for example, of the channel, right? You also are dependent on what's the relative strength of your noise, right? The higher the noise, the poorer the signal quality is, because we know that it's going to have a lower signal to noise ratio, as we already said. You also, the signal rate also plays a role here. Now, when we talk about signal rate, we're mostly talking about at the rate the information is delivered. And this is what we call bits, right? And because most of our um, communication is digital, is how many bits per second or bits per unit of time you get, right? So we want to know how many bits can be sent over channel per second. Now, there's a delicate balance. There's always these trade-offs that we're doing in all of these uh, type of systems. So the fundamental parameters and physical limitation that control the connection rate and signal quality are both the channel bandwidth, okay? So channel bandwidth and signal power, okay? So the bandwidth of a channel is, remember, the range of frequency. Okay, for the channel, we're talking about the bandwidth of the channel, okay, of the channel, is the range of frequency that it can carry with reasonable fidelity, right? It's not the same to send a signal of 1 megahertz than to send a signal of, let's say, 100 megahertz, right? You can send more information per unit time at 100 megahertz, but if your channel is corrupting your signal, it doesn't work, right? Um, Now, how do we talk about and determine what the channel bandwidth is, right? So let's talk about a simple example here. Let's say that you have a frequency or signal, excuse me, whose frequency varies between 0, which is DC, up to 5 kilohertz. Then in that case, you need a channel bandwidth B of at least 5 kilohertz, right? Anything less than that, and you are limiting your signal and the frequency extent. You can't go past 5 kilohertz, right? Remember that every signal has bandwidth, and that's the maximum range of its frequency components. The faster the signal, in some cases, the higher data rate, right? That's what it translates to. The higher its maximum frequency, and the larger its bandwidth is, okay? So faster signal, higher bandwidth, therefore the channel bandwidth has to be higher as well. Okay, so a signal will be successful to be transmitted through a channel if the channel bandwidth exceeds the signal bandwidth. And that this is a requirement that, for example, for wireless, you can feel fairly confident depending on what part of the spectrum you are, that you can meet that, right? Um, most of the time. There are certain frequency ranges where the attenuation is so much that you probably um, for, like, let's say, point-to-point communications and that sort of thing, you do not want to use a certain frequency range. Okay. Um, it doesn't mean that they are never used, right? Because fairly popular is the 60 gigahertz, right? 60 gigahertz attenuates signal a lot because that's the resonance of, if memory serves, of oxygen, right? So if you try to send something with oxygen, it doesn't get very far because it gets attenuated. However, if you're in space and, for example, you want your moon base to communicate back to the International Space Station, that's fairly good to do because on the ground on Earth, they will never hear you at 60 gigahertz because it doesn't make it through the atmosphere, right? Because of the oxygen content. So there are uses for it. It's not that we never use them, right? And that's a wild example, right? We don't have a moon base yet. Now, the signal power plays a dual role. Signal power is kind of interesting. And remember, signal power is something that for most applications, or a large set, I shouldn't say most, for a large set of applications, we're under control. We know what kind of power, and we can play games with the power, okay? So there's a direct relationship to the quality of the transmission, the power level, right? Increasing PS strengthens the signal, right? And suppresses the effect of the channel, noise, and interference, right? So going back to signal to noise ratio, right? The higher the signal to noise ratio, the better quality signal you have. It's really that simple. It doesn't come for free though, right? So to begin with, if you need the higher the power of your signal, that means the more power you have to put into the system to get that power out of your signal. So you need more power, right? And your the power company makes more money off of you, right? Um, so the larger the signal power allows the system to maintain that minimum signal to noise ratio over a much longer distance. That's what it does, right? So the higher the power, the higher your signal to noise ratio, the longer you can go with it, right? The longer distance. The second role of the signal power is not as obvious, right? If we go back to information theory, the channel bandwidth, right, and the signal power are somewhat exchangeable, right? You trade one for the other, right? So if you want to maintain, okay, if you want to maintain a given rate, a given data rate, and accuracy of your information, right? You can trade both power and bandwidth. So you might use less bandwidth if you're willing to increase the power, or if you have to reduce the power, then you need a bigger bandwidth. And again, this is not gets back to this is a trade-off, and it's a trade-off between bandwidth and power. Okay, remember that if you increase the bandwidth, you're also increasing your noise, so you're exposing yourself, right? Again, signal to noise ratio is this delicate balance between the two. Okay, so let's take some time to talk about channel capacity and the data rate. So we know that channel bandwidth limits the bandwidth of the signals, right? So if the channel doesn't have enough bandwidth or is going to begin to cut off your signal, you're going to have problem with the signal bandwidth if it's greater than that, right? So, so for a successful signal, normally we require that the channel have a larger bandwidth than our signal, right? So signal to noise ratio and bandwidth can both affect the underlying channel throughput, right? So the peak throughput that you can send to the channel, or the maximum, we call it, I called it peak here, but peak or maximum throughput, if you want to call it that, right? Whatever that maximum is what we call channel capacity. So a channel has a certain capacity. Um, One of the most commonly encountered channels is the one that we call the additive wide Gaussian noise channel, or AWGN. And that's exactly what it stands for. It's a channel that allows you to send anything through it, but it's going to add this Gaussian noise. Now, for those of you that know probability, it means that the noise in the channel, and most wireless channels are like this, have a noise that follows a probability distribution function that's Gaussian in nature, which Gaussian has a certain shape. Okay, so we assume that the AWGN channel, or the Gaussian channel, has no distortion. It doesn't distort your signal, i.e., it it has finite bandwidth, but it's enough bandwidth for your signal, right? So the ideal model, okay, let me stress this. I want to stress this thing about it's an ideal model, okay? Practical application cases with distortionless channel and provides performance upper bound. So this is going to be an upper bound for a general linearly uh, distortive channel, okay? And we owe this to Mr. Shannon, right? Mr. Shannon came up with the Shannon limit. You'll hear this a lot, right? So for the Shannon limit, the maximum capacity, or the capacity of your channel, okay, capacity C is B log 2 of 1 plus the signal to noise ratio. And the results, conveniently enough, comes out in bits per second. Now, in the Shannon equation, please remember you have to put the linear ratio. SNR has to be linear ratio, not in dB. Okay? So remember, if you want SNR in linear terms, right, it would be SNR would equal 10 to the SNR in dB, right, divided by 10. Okay? So remember to do that. Convert it back to linear units, and that's the SNR that we will use in this formula to calculate the channel capacity. Remember, it's the upper bound. This is the upper bound. This is the maximum that you can do. Rate, and it's the upper bound of the rate of information. Okay? So on the flip side of that, what that means is it's impossible to transmit at a higher data rate than this. Again, it would be impossible to transmit at a higher rate than C, okay, without incurring in a large number of errors. So yes, you can go past the Shannon limit in your channel, but then you have to expect, right, much more errors, right, or errors in general. So it clearly shows, the Shannon's equation clearly shows that there's a limit, right, that is jointly imposed by the bandwidth and a signal to noise ratio, which goes back to our discussion of power and bandwidth trade-offs, okay? And notice that Shannon only points out to a rate limit, okay? So it just tells you, it doesn't tell you how to realize it. It doesn't tell you anything else. It tells you this is your limit, okay? In fact, certain communications would be possible, right? Uh, so certain communication would be achieved only with a system with a very large and impractical complexity, right? If you try to go sometimes way too close to what Shannon limits is, or anything else, right? So in practice, right? In practice, systems operate at rates that are below the Shannon rate, right? So we don't really try to go all the way up to the Shannon limit to say, oh, we're maximizing our channel. We normally don't do that, okay? That would be too complex, okay? So in conclusion, Shannon's equation kind of shows us in a qualitatively way the basic roles that both band and signal to noise ratio have in limiting the performance of a communication system. Okay, so let's see an example, something that's kind of practical that you might run into if you're working for, let's say, some telecommunication company. So let's say Some field engineer takes a series of measurements at the same location for 10 days, right? Here's his measurements. The results, the channel bandwidth of interest that we're working at is 5 megahertz, okay? Oops, sorry. So let's say, okay, 5 megahertz. So let's say that we want to calculate the maximum ideal channel capacity. Notice that I said maximum, and I want it in megabits per second. And let's do this using MATLAB or Octave, right? Let's a little bit of coding so we practice. Okay, so here's our data, and here's the code. Now, I start off by on line number 3, putting out Boltzmann's constant. The problem specifies a bandwidth, so I put that on line number 4, 5E6, right, for 5 megahertz. Then I capture the field data, starting at line number 8. Notice that I called this variable data in, okay, data in, and because it's data, I went ahead and just typed it in, right? Notice that my famous 2 columns, okay, of data. Not too bad. It's to enter the data this way. I then calculate the power. I called it input power, right? I could have called it measured power. You can put a name that makes sense to you. And then notice how here, when I call data in, I call the second column. That's why there's a 2 here, okay? Right here, there's a 2. The reason for that 2 is because I want the second column, right? I then calculate the noise. I know the temperature is the first column, right? If you go back to the data, right, it's temperatures in degrees Celsius, right? That's the first column of data. So that's why there's a 1 right here, okay? And notice that I take data and I add 273, right? And then I do Boltzmann's constant, that's K, times the temperature times the bandwidth, okay? Now the signal to noise ratio, everything so far is in watts. I have not converted to dB. So therefore, signal to noise ratio, I have to divide. Okay, so we divide here, and then here's where we're going to calculate it in bits per second. All right, notice that I called it in line 24 C equals C underscore BPS. BPS stands for bits per second. To convert it to megabits per second, I have to divide by 1 e to the 6. Okay. Normally, we talk about signal to noise ratio in dB. The problem did not call that out, right? Calculate the capacity, right? It doesn't say much else, but let's go ahead and calculate it in dB so that when we create our table, and here's again my approach to creating these 2 column data or column data, right? I put signal to noise ratio and the capacity in megabits per second. The typical fprintf to print my table, hit run and the code, and then you end up with this table, right? Now, the cool thing about this example is it shows you that you can go out in the field and it's always the same channel, it's always the same transmitter, or is it? Okay. Remember a little while ago I said we are always sort of in control of the transmitter. We're never in control of the channel. So this is a wired communication. He goes to the same place and measures day over day over day, right? Each day he measures. Let's say he measures at the exact same time. Let's say we could actually say that. But you can see that the signal to noise ratio is changing. Why is that? Because the channel is different every day. Maybe some days it's raining. Maybe some days it's more sunny. Uh, the temperature is varying, right? Not every day has the same temperature. We say nothing of, when you look at the temperature, it actually, you see it varying, right? It stays around some certain average, but it does change. And that temperature change is changing your noise power, therefore it's changing your signal to noise ratio, amongst other things, right? That might be impacting your signal. And so at the end of the day, our channel capacity varies daily due to all these circumstances. And you can see like the first 5 days, we kind of had a lower capacity than the last 5 days, right? So it seems like we were a little bit um, hotter in the last few days, maybe, but our signal variance kind of worked in our favor. Okay, all right. And remember, this is at the receiver. So wherever he's measuring, let's say that that's where his receiver was, and he's using this receiver to make measurements. Okay, all right. So now let's talk about this concept of modulation. Now, normally analog signals or our baseband signals, right? This is the stuff that comes after that analog to digital converter. Those signals are low pass in nature, and we've mentioned this before, right? So it goes from 0 hertz to some maximum frequencies. Now, the thing about baseband signals, especially if you want to send them over the air, they're not compatible with the channel, right? So baseband signals are pretty good for things like cable, for example. You can send baseband signal through over a cable. Why not? I mean, a cable will, this is how we build our circuits and other things, right? We have traces that on the PC boards that are analogous to cables or wires, etc., right? Now, depending on the channel, now let's talk about the wireless channel, your signal is not always suitable for direct transmission, right? So when the signal and the channel frequency band don't match, the signal needs to be modified. You can't modify the channel. You see, the channel is immovable, right? You can't really modify the channel, right? Sure, you can if it's a cable like in cable TV, you can go and swap out the cable, right? Why not? But you really over the air, you really have no control over that. So you have to make the signal compatible with the channel. That's the uh, most of the time that's the way it works. So, and this conversion process is what's known as modulation. Now, modulation has other implications, but the main thing where it all started, and one of the main reasons we do modulation, is to make our signal compatible with the channel. Now, in the modulation process, what happens is the baseband signal, right, is used to control, right, control or modulate, right, some parameter of a radio carrier, okay? Radio carrier. And we're back to the concept of a carrier. Remember we were talking about the message and the guy gets on a horse and he's carrying the message, or he's your carrier. Your postal uh, person is also a carrier, right? Sometimes we actually call him the postal carrier or just a carrier, right? Or mail carrier, right? What is a carrier supposed to do, right? A carrier is supposed to carry the message from point A to point B, right? And it's not supposed to change the message along the way, so that the message that was originated at the transmitter gets to the receiver unchanged, right? Remember what the purpose of the communication systems is? Output message, right? The input message is equal to the output message. That's it. That's it. The carrier cannot change it, or we hope it doesn't, right? Now, here's what modulation is. The carrier, okay, the carrier that we're talking about is a sinusoidal at a high frequency to make it compatible with the channel, right? So, and we'll talk about this in a little bit more. But through modulation, what you're going to do is you're going to change some of the parameters. Now, this signal, which is shown here as A, right, has three properties that you can talk about. You can talk about the amplitude, you can talk about the frequency, or the phase. So if we make any of those vary in proportion to our baseband signal, which we've been calling M of T, right? then you can have one of three types of modulations. You can have amplitude modulation, FM modulation, or phase modulation, which is PM, right? So in AM modulation, the amplitude of the carrier, amplitude, because that's why it's called AM, will vary linearly in, with respect to MFT. So let's say that in this chart from our textbook, from Lathian Ding, let's say this is MFT, this signal, right? The signal here B, right? Now notice how the AM waveform, right? We're going to impose this onto the carrier, and we end up with what we see in C. Notice that as the information signal goes up and to the positive side, the amplitude of our carrier increases. As soon as it starts to go down and even goes into the negative side, the signal of our carrier becomes lower, right? So look, this is the minimum point of the signal. That's the minimum amplitude. Here's like the maximum level of our message, and that's where the carrier is maximum. The same thing happens with FM, which is D here, except that now we're changing the frequency. We're going to leave the amplitude constant, but we're going to change the frequency. And you can again see, if you're careful enough, right, when you have the peaks of the signal, right, of the message signal in these areas, that's where the frequency is the highest, because you can see how close are the different what you call the peaks and valleys of your signal. And then you can see how the signal spreads wider in time when the signal or your message signal is the lowest. FM and PM are hard to tell apart, right? In an example like this with a message signal like this, that's why most likely the authors didn't put a picture of AM, PM, right? Because they look very similar in this case. So to transmit, for right to the transmission, right, to transmit the signal over a wireless channel, we already had mentioned that we have to convert it to an electromagnetic wave, right, to be able to transmit it. And the transducer that does that is what we all know as an antenna. Now, to do this efficiently, the antenna should be on the order of a fraction or more of the wavelength of the signal, right? And the wavelength of a signal, right? If I were to look at this and say, what's the wavelength of my signal? If I were looking at it on the oscilloscope, is the same, the wavelength would be the period. Except that when we're talking about transmitting the signal through space, we talk about that same wavelength in terms of distance, right? So the wavelength would have units of meters, for example, right? So you start transmitting it. How long does it take for the signal, or how long does it travel, right, before you see another, let's say another peak, right? So from peak to peak, in terms of distance of the signal travel, that's what we're going to call the wavelength. And the formula couldn't be any simpler. It's one of these formulas, right, that has just three parameters and not very complicated. Okay, so here's our formula. So C equals lambda. Lambda is the wavelength, and F stands for frequency. Now C is the speed of light in free space, which is this really long number. If you want to memorize it, go ahead. Or in many of our hand calculation, we just use 3 times 10 to the 8, and the units are meters per second, which is a speed, right? So that's the speed of light. Now, we already said that the antenna has to be kind of proportional to the wavelength, right? So this is why baseband signals are not compatible with the channel, right? One of the reasons is their wavelengths are just too large, right, for a reasonable antenna. Why do we say that? Let's look at an example, right? Let's say audio, like you guys are listening to me right now. It sits in a frequency range between 100 and to like 3,000 hertz, right? If I convert that using our formula up there, you'll see that that ends up being anywhere from 100 to 3,000 kilometers. You're not building an antenna proportional to that, right? That's just way too large, right? Even 100 kilometers is out of the question. All right. Um, so so what we do is, right, this is where modulation comes into play, right? Because now the frequency that we're talking about are frequencies in the region of the carrier. So let's say we have a carrier, right? For example, we have a carrier that is 100 megahertz. Now the wavelength is only 3 meters. 3 meters we can deal with, right? In fact, you can transmit 100 megahertz with an antenna that's about 1 meter, okay? Which is long, about 3 feet long, right? All right. So keeping with our theme of transmission, let's look at what happens when the signal, this electromagnetic signal that we have put on or sent out of our antenna, what happens to it, right? So what happens is you start off, let's say, with a signal. Let's say this is your antenna here, where we have this S, right? Now, after it travels a certain amount of time, let's say a distance r, r here is kind of arbitrary, but it travels a certain distance r, and we have the signal, right? We're looking at it, and it occupies a certain area, or we're studying this certain area, right? It could be 1 meter square or whatever. It's an area A. Now, we're going to keep track of this. Now, what happens is as the signal is traveling in distance away from the antenna, right, it sort of spreading in space. That's what happens. That's how you get this. That's why you get so much loss. So at 2 times the original distance after we looked at it, that same rectangle that we were looking at, which was A, has grown in size 4 times. So we double the distance and this grows by 4. We triple the distance and now the same area occupies 9 times the area. If you look closely, you're having a square increase in area, right? Now, the area that initially we were talking about had a certain power level. That power level is being spread across space. That's what this means, okay? And how do we account for that? We actually account for that as a loss, right? And we call that free space loss. Remember, we're looking at a small cut here, but the antenna in theory is transmitting an entire 3D space, right? But our receive antenna is only going to intercept that at some point, and it's just going to get a small cut of whatever that 3D sphere is originally. It doesn't get the whole 3D sphere. Okay, if you think about it. So let's say it gets one of these small rectangles at the end of the day. That's why you'll hear people talk about antenna apertures. That's exactly what I mean. That's how much area it intercepts of the signal. All right. So there's a simple formula for this free space loss, as we call it, right? And we abbreviate it with FSPL, right? And because it involves the surface of a sphere. That's where the 4 pi r comes from, and r stands for distance or radius. And notice that lambda, or the wavelength, is also a parameter here. And because we know how to convert from lambda to frequency, or we know that lambda depends on frequency and the speed of light, you can also see its effect in here, okay? And the square term, right? The square term is because we know that every time you you double the every time you increase the radius or the distance, the area grows by the square of whatever the distance is, right? We can, and we normally do, express free space loss in dB. I'm not going to go through all the equations and how we process these, but at the bottom line is there is a constant term, right, at the end. So we end up by noticing that at the end of the day, the free space loss depends on both the distance and the frequency, right? It depends on both the distance, r, and the frequency. Those are the important parameters. Okay. All right. So now we know how much power we put into our antenna on the transmitter side. So how much do we get on the receiver side? We don't know. Well, we can't calculate it, and it's not that difficult, right? So if I know the power that's transmitted, right? That's how much power I send into the transmit antenna. This antenna is characterized by a certain gain, or the gain of the antenna, G sub t, right? Let's say it's direct line of sight, and we talked about direct line of sight. It actually means that, right? You can see something, no obstruction, right? After a certain distance r, we are going to have our receive antenna, that our receive antenna has a gain sub r, and we are interested in knowing how much power will our receiver see. Well, that we calculate using Frisk's formula, which is right here, right? So the power received depends on how much power you transmitted, P of t, multiplied by the gain of the transmit antenna, by the gain of the receive antenna, G sub r, divided all by free space loss. And like every time you see an equation like this in a ratio, free space loss here is the linear, not in dB, right? And again, we can do some math, and we can reduce this and express it all in dBs as the equation here in the bottom, right? So if you're working with linear quantities, you use this one. Let's call this one number 1. If you're working with dBs, then we use equation number 2. Okay. Question: what are the units? This is of PR, right? If you recall, free space loss is a loss, and losses don't have a unit list. Gains are unitless. So the only thing that has units here is P of t. Same thing here. The only thing that has units is P of t, right? So if we're working in linear units, you're normally either working in milliwatts or watts. And if you were working in dB units, then it would be either dBm or dB watts, right? Be consistent, okay? So, and make sure that when you're talking about power, you put your units either dBm or dB watts. So let's say that now we want to increase our capacity, right? So if I only transmit one signal to the channel, um, I can only charge for that one service. What if I could do more than one, right? In the same channel, right? Um, that's where multiplexing comes in, right? So the channel, remember, is always going to be limited by the signal to noise ratio and the bandwidth, right? Signal to noise ratio and bandwidth is always limiting the capacity of our channel. Now, how do we increase the number of people or number of uses or users, right? Right. We do that by combining. So multiplexing refers to a combination of signals, right? So let's give an example. Let's say you have TV, simple TV, right? If I can only have a one TV channel, right, go through the air, then uh, that means everybody has to watch the same program all the time, and everybody has to agree, right? That's never going to happen because you can only broadcast one TV channel. Now with multiplexing, right, or without multiplexing, that's what you're limited to. This is really wasteful because the channel bandwidth is typically for the TV is way wider than whatever the TV signal is, right? So that means there's a lot of bandwidth that would be wasted. One of the nice things about modulation, right? One of the nice things about modulation is that it allows multiple signals to be transmitted at the same time in the same geographical area without direct interference with each other, right? So this is one of the properties of modulation. This is why you can have different TV channels because you modulate the signal onto different carriers at different frequencies. And as long as these frequencies are sufficiently far apart from each other, they will not interfere with each other. Now, what that means is at your receiver, in this case, the TV set, you need some kind of bandpass filter, right, centered around your frequency so that you can block the rest and only receive the one that you're interested in. Now, when you change the channel, that means that this bandpass filter, right, then selects a different carrier frequency, and therefore you're seeing a different channel. What do we call this? This is what we call frequency division multiplexing, right? So through the same channel, we're going to send simultaneous signals, right? We send them simultaneously, and they have to be, right? They have to be non-overlapping. That means you look at the bandwidth of your TV signal, right? And you make sure that the next one that allegedly is going to have about the same bandwidth, you're going to separate them so that the bandwidth, no part of these signals overlap each other. And you have what's known as frequency division multiplexing, and we abbreviate that with the acronym FDM, right? So whenever you hear talk about FDM, now you know what that means, right? And that's how you get all your channels on your radios, TVs, etc. Now, we talked about modulation. We haven't talked about the process that undoes the modulation, which is demodulation, right? Once you select the desired signal, you have to convert it back to baseband form, right? Notice that if we're going to, at the receiver, before you demodulate, you need that bandpass filter, right? And you need to select the right modulated signal in order to have that process, right? And see the channel that you're interested in. So once the modulated signal has been isolated by the filter, we are going to pass it to a circuit called a demodulator that will then convert the modulated signal back to our baseband signal voltage, right? And we know that there's three basic schemes like the AM, FM, and PM. So our demodulator has to correspond to whatever modulation we use initially to transmit. So if you modulate an AM, you demodulate an AM, which kind of makes some sense, right, to do that. But let's make sure that we understand the concept. We go from AM to AM or FM to FM, right? So these things have to be compatible with each other, right? Um, about it. Now I'm going to talk about digital source coding and error correction. Kind of the same way we did demodulation, just briefly. Later on in the course, we will not be covering much more than this, but it's worth talking about it so that we all understand that these systems, in order to work properly, digital systems are an eternal battle between source coding and error correction. That's where most of the battles and most of the advances have been, right? So a digital system is always trying to be as efficient as it can be, right? How do you become efficient? Well, you want to send a message as fast as possibly can with the least data, right? If you can reduce the amount of data, digital data that it takes to send a message, that means you get it there quicker. Therefore, you're increasing the throughput, the capacity of your channel, right? That is the function of source encoding, right? Aims to generate the fewest bit possible without sacrificing bit errors, right? You don't want bits to be an error, right? If it was a 1, all of a sudden you receive a 0, or if it was supposed to be a 0, you receive a 1, right? You don't want to create errors, but that's what this encoding does. However, on the flip side of that, to deal with errors, right, that arise from noise, distortion, other interference, you need certain level of redundancy, right? So, okay, I sent you a bit. That's boring, right? I sent you a bit. Now, if you send a bit, right, a group of bits, right, and they have a certain dependency between them, even if one of them gets there in error because there was certain dependency, that is a code, and this dependency can actually correct for the bit that was wrong, right? Um, One of the things that they do for this is they do like this differential encoding. So instead of sending the bit, 2 bits, you send the difference between the 2 bits, and you're constantly doing that. So when the difference doesn't agree, you know that you had a bit that is incorrect. Okay, that's at a high level. Let's not get into way too much of the detail. Okay. So source coding and error coding are two successive stages. Isn't that curious, right? They're successive stages in the digital communication system, right? And they are always a trade-off, and you're always looking for the best performance, right? Like I told you, a lot of the advances that we've done, right? This is where the battles are fought, is between source coding and error correction, right? I want to send it fast with the least amount of bits, but I also want to make sure that the bits that I get are correct, right? Uh, so source coding is always aiming to use as little bandwidth as possible, right? You want to use as little bandwidth as possible. But error correction intentionally adds more bits, right? To avoid or help the detection, the correct detection, right? The key for error correction is that it wants to make it correct most of the likely errors. Okay. Now that's what I'm going to say for error correction. This is the end of our part 2 of this lecture. If you want to know a little bit more about this, please read section 1.6 of the textbook. Thank you, and I'll see you in our future lecture number 2.